Okay, so welcome back, everyone. So today is my pleasure to welcome Cornelio Cristina, who will be giving the second lecture on AI-Descartes and AI-Hilbert. And today she will talk about derivable scientific discovery with AI-Descartes. Yeah, thank you, Cristina.
Yeah, thank you for inviting me and all of us to give this series of seminar on scientific discovery. So today I will talk about the second part of this series that focus on the paper of AI-Descartes. And then next week, I believe, Ryan will talk about the third part, that will be the AI-Hilbert. So to start, I want to just give a quick summary of what has been said in the last lecture. So we started by looking at the scientific method, and we look at how it works. So here is a kind of schematic, like a summary, high-level version of how it works, and probably all of you know how it works. So usually the scientists start with the hypothesis generated from theory. So start to generate new physical law or chemistry law, looking at the theory that the scientist knows, and then try to test this hypothesis on data. So, and this is done in a loop until the scientist is satisfied from the new formula that has been generated. But there's been evidence that even though during the years, following the classic scientific discovery method, even if during years the number of scientists is increasing, so the effort put into scientific discovery is increasing, the number of outcomes of this research is decreasing. So the question that arises here is that are they all low-hanging fruit of scientific discovery already taken? And is the scientific discovery enough? So the research question is, can we evolve also beyond the scientific method? So lately, I mean, the last, let's say, few years, in quote marks, machine learning kind of developed us sort of a new scientific method. So you just look at the data and produce new hypotheses just from the data. And this seems to work well if we have a large amount of data and if there is no domain knowledge that we can exploit. So, but the problem is that these methods, they're often hard to generalize beyond the data that we are observing, so the so-called auto-distribution data points, and also they're not really interpretable. So for us, this was like input for developing new techniques on combining data and theory for making new discoveries. So what we're looking for is discover scientifically meaningful formulas. So, and what do we mean with meaningful? So meaningful is that a formula is meaningful when it's both consistent with the known theory, but also fulfill the data. So it's accurate, empirically accurate. So, and why we want this? Because in this way, the formula is not just accurate, but are also kind of appealing because they are predictive also for the auto-distribution points. So they generalize better if they also obey to a known theory. And the other capabilities that we want for the new discoveries is that they can be verified. So ideally, we want to have a formal proof that a formula is derivable from the known theory, and even if in the case that is not derivable, then we want to have a sort of quality measure. So how far is the formula from the theory we already know? And just to give you an idea of what I mean with theory is, for example, if we take a physical phenomenon like the orbit of planets around a star, the known theory, there can be well-known laws like a conservation of energy, the definition of the center of mass, and so on. So in this series of work that we've been doing, we developed two new scientific methods. So the first one, what we called AI-Descartes, is similar to the classic scientific method, but it flips the hypothesis and the testing. So now we generate the hypothesis from the data, which is similar to machine learning-based scientific method. And then we test on the theory, while the classic scientific discovery method is the other way around. So the hypothesis is generated from the theory and the testing is done on the data. So, and also for AI-Descartes, we do this in a loop until we are satisfied for the new formula and some satisfying criteria are met. And the second scientific method that we introduced is AI-Hilbert. So for this one, we combine these two components, so the hypothesis and the testing. So the hypothesis and testing is done together at the same time on both the theory and the data. So this is done simultaneously. And from that, we generate a new formula. So just to give you a little bit of kind of very high-level overview of the two methods. So the first one, AI-Descartes, is the one that I will be explaining today, and use symbolic regression to extract the formula from the data, and then use logical reasoning to select which one of the hypotheses is closer or is even derivable from the set of known laws that we know about the environment where the phenomenon is observed. The second one, AI-Hilbert, so this one combines polynomial optimization and logical constraints to derive a formula that is both consistent with the theory and is empirically validated. And about this, Ryan next week will explain a little bit more details about this method. Okay, so now we can start with the kind of the talk of today. So the main part. I will just give first a quick overview of the AI-Descartes system. So we start with the numerical data and the background theory. So these are the two main input of the system. So from the numerical data, we use symbolic discovery to generate an ordered list of hypotheses. And the list of hypotheses is ordered by error on the data. So how close is the formula to the numerical data. So then we use the background theory, and together with the list of hypotheses, we input these two components to the reasoning part of the method. And the reasoning part is has the role of re-ranking the list of hypotheses. So we take the order list of hypotheses that was ranked based on the error on the data, and we introduce another type of error, which is the reasoning error, to then produce the formula that is both compatible with the background theory and numerical data. And this formula will be then used for predictions. So this is a kind of simplified version of the system. The whole system is a little bit more complex than that, and has also other components like experimental design and abductive reasoning and so on that I will not be discussing today. So the two main components that we are talking, that I will talk about today. So is the symbolic regression part and the reasoning part, especially for the deductive reasoning. Okay, so what is the system input? So it's a tuple of 4 elements. So we start with the background theory, which is just a collection of axioms. And the axioms are logical formula. They can be also differential equation, or just a set of known laws that we know they are true about the environment in which we are observing the phenomenon. And we make 2 assumptions. One is the completeness assumption. So we have all the axioms that are necessary to explain the phenomenon, and the consistency assumption. So we want that all the axioms do not, so they are compliant with each other, so they don't contradict each other. The second element in the system input is the hypothesis class. So this consists of a grammar, so a set of mathematical symbols symbolic models that we want to allow to be discovered. And then a set of invariant constraints. So for example, we don't want to generate two formulas that are equivalent, for example, x plus y and y plus x. And the last one is a set of constraints on the functional form. For example, we want the formula to be monotonic or not, and so on. Then another component of the input is the data. So this is just a set of n data points, or some examples that we observed on the environment. And the last one is a set of modeler preferences. This is a set of parameters, for example, error bounds on the accuracy, or error bounds on like intervals where we want a certain value to lie in. Okay, so the first component of the system that I mentioned earlier is the symbolic regression. So this component is based on a grammar. So the grammar has to be defined because based on the grammar, we can define the set of all possible type of formulas that we admit, and we want to, the functional forms that we want to discover. And the grammar is based on a set of operators. For example, we have the plus, the minus, the product, and so on. A set of variables, and a set of numerical constants. So then we represent each formula with the parsing tree. So for example, the formula that we can see here on the right can be first expanded. So this formula here can be expanded, and this one can be transformed in this tree, where we have the first operator here plus, and then we have the exponent, and so on. So, and why we're doing this? Because this can give us a definition of how complex the formula is. For example, if we look at the depth of the tree, we can say that this formula has a rank of 5. But we can also use other measures that for the complexity. For example, we can count the number of operators, the number of constants, the number of variables, and so on. Okay, so then this is the space of the formulas that we are considering. And now that we define the space, we can formulate the symbolic regression as an optimization problem, where we want to minimize the error on the data while keeping the complexity of the formula bounded. For example, we want all the parsing tree of maximum depth of 4. And then we want the formula to obey to the grammar that we defined before with the operators and variables, constant, and how to create sentences out of this basic bricks of the grammar. Then we also have like the symbols that we want to use, a set of invariances, and finally a set of non-numerical, non-linear numerical expressions. These one are some constraints. For example, if we want the formula to pass through 0 at when all the variables are at 0, or some constraints like that. Okay, so and once we solve this problem, then we have we produce a set of hypotheses. All the hypotheses are ranked based on the fidelity on the data. And the question now is, how do we choose between this set of hypotheses? Because they are all very close to the data, and they all with a bounded complexity. So to choose between the set of hypotheses, then we introduce the second component of the system, which is the reasoning component. And we develop several different capabilities that help us to understand which of this formula that we generated with symbolic regression is the best one. And with best one, I mean the most meaningful. So the one that also obey to the laws that we know about the phenomenon, the environment that we are considering. So the first capability that I'll talk about is the derivability. So this one, we want to know if a formula can be actually derived, logically derived from the set of axioms defining our background theory. So this is the strongest capability. So, but the formula is not always derivable. So then we want to define a set of reasoning measures. So the reasoning measures are measures that tell us how far this formula is from the background theory. So how distant it is. And I will talk more in details about this later. Then we also have some other capabilities like counterexample generation. For example, if a formula is not derivable and is contradicting some of the axioms in the background theory, then we can use the reasoner to generate new data points that violates the formula. They violates the background theory. And the last one is what we call constraint preprocessing. So this one, so we want to check if the formula obeys to certain laws that we know, but they're different from the background theory. So the constraints, they focus on the functional form. So for example, we can ask for monotonicity, condition at limit, or if in zero, the formula go through zero. While the background theory is different because it can, first, it can involve variables that are not observable. And second, doesn't focus on the functional form, but it can describe other phenomena that are present in the environment, for example, conservation of energy or the definition of the center of mass. So this is the main difference between constraints on the functional form and background theory. Okay, so let's talk a little bit about the derivability. So this, just to give you a very high-level idea of what I mean with we want to find a derivation of a formula. So, for example, here we can see the orbital speed equation. And this is the very simple background theory that describes the environment where this formula is observed, like this phenomenon is observed. For example, we had the definition of gravitational force, kinetic force, and the condition at equilibrium. So the derivation here is, for example, we start with the third axiom. So we look at the condition at equilibrium. Then we substitute the gravitational force with the definition of the gravitational force, which is the second axiom. And then we can substitute the first axiom. So then we can simplify the R and so on until we can reach the final formula of the orbital speed. So this is kind of what I mean with derivation. And so how we generate this derivation. So the example that I showed you is very simple, but if we have bigger background theory, so then we cannot do it by hand because the search space is too big. Then we are looking at a reasoner that they can help us to produce this derivation automatically. And some of them are well known, like Mathematica has some derivation capability. There are some library in Python, like SymPy, and then we have more classic logic prover, like Prolog or Datalog. Then we have also some theorem provers, like Beagle and Chimera. So they are all described in different type of logic or different type of like equation or formulas that they can process. And for this work, we focus on Chimera. So this one is a theorem prover that is used mostly for a hybrid system and combine different type of reasoning. For example, we can have we have usually deductive reasoning and as an underlying CAD system. So in our case, we use Mathematica as a CAD system. But we also use Mathematica for other type of other reasoning capabilities. If you remember before, I mentioned the constraints preprocessing. So for this one, we use Mathematica because it's a little bit simpler, because we are just looking at the functional form, like, for example, to check if a functional form is monotonic. While for the derivability, we need something more like a theorem prover, like Chimera. Okay, so just to give you an idea how Chimera looks like, so we first define our problem. So this is the one that I showed you before. So this is defined in a specific syntax that is then ingested to the theorem prover that will, for example, say, okay, this is provable. So then we have, so this formula can be deduced by the set of axioms. And then for like other cases, it can also produce derivation. So this is an example for differential axiomatization of the pendulum. So this is looks a little bit more complicated, closer to the derivation example that I showed you before. Okay, so but which type of the derivability are we using? For this work, we use two different types. So the first one is what we call direct derivability. So we want to know if a formula can be deduced by a set of axioms and a set of constraints. And this one, for example, is very useful when we have formulas that do not have any numerical constant. So, for example, here on the left, you can see an example of what we are trying to prove. For if we have this functional form, like the function f is equal to p divided by numerical constant times p plus another numerical constant, the direct derivability check if the set of axioms, so what we know about the environment, plus a set of constraints, for example, the masses has to be greater than 0. If this conjunction implies our formula. But this is very difficult if we have exact numerical constant, because this one will probably have some numerical error, so will not match exactly the constant that we have in the background theory. So then we introduce this second type of derivability that we call existential derivability. So what we are trying to do is to check if there are two, in this case, in the example on the left, if there exist two numerical constants that will allow this implication. So if two constants exist such that the set of axioms and constraints implies our formula, and we don't care about the exact number of the constant, because later on we can refine this number looking at the data. But what is important here is that this formula is derivable or not from the background theory. So this is kind of like a weaker type of derivability compared to the first one. And we are using it just to deal with maybe some little numerical error in the constant, while still being able to prove if a formula is derivable or not. Okay, so but then what happens if a formula is not derivable? So then we want to try to find the distance of the formula to a derivable formula that is implicitly defined in the set of axioms of the background theory. So you can imagine like our formula generated from the data is the green one, but on the data, we just observe these 3 data points. So then probably, so this one is not generalizing well beyond these data points, right? But if we consider the background theory, if it's complete and consistent, then is it possible to derive a formula from the background theory that is the ground truth formula? The problem is that we don't have the ground truth formula, but we have the set of axioms that might generate it. So if we, from the set of axioms, generate all the possible formula that are that can be deduced from the set of axioms, then the ground truth formula will be one of them. But the number of possible formula that can be derived is infinite. So we cannot generate them all and then find the one that approximates the data. But we have it implicitly defined. So then we can use a theorem prover to check the distance between the green function here and the blue function without knowing the functional form of the blue function, because it's implicitly defined in the background theory. So we then defined three different types of what we call reasoning error. So let's start with the first one. The first one is the pointwise reasoning error. So for this error, we basically look at the data points. So we look at this distance between the two functions, so the green one and the blue one, in the data point. So then we can use different norms like L2 or L infinity. But if we look at L2, for example, we can see that we are computing the distance between the two functions. The first one is the one that we generated from the data, and the second one is the one that is implicitly defined in the background theory. So, and we can do this with a theorem prover without knowing the second, so the functional form of the blue one. The second type of error is the generalization reasoning error. So we ask ourselves, okay, so our formula, it works very good on the close to the data points that we observed in the environment. But what happened between the data points? So then we can use this generalized reasoning error, and we can define these intervals, for example, x1 to x2 and x2 to x3. And then we can say, okay, between the minimum of those, so x1, and the maximum of those, x3, compute the maximum distance between these two functions. So this is basically what we mean with generalization reasoning error. But then we also want to know how our green formula here, the one that we generated on the data, how it works beyond these intervals that we saw in the environment. So for this reason, we also consider what we call the variable dependence. So we increase the magnitude of the order of magnitude of one variable at a time, make it either very big or very small, and we want to calculate the maximum distance between these two formulas in this case. So then we can see that, for example, if for a variable, if we increase the value of this specific variable, how the error increase. For example, if the error increase exponentially or it increase linearly. And so this can give us a little bit of a hint of what we did wrong for that variable. Because if we increase the value of a variable and the error does not increase, then probably the variable in the functional form is fine. But maybe if it increases exponentially, then maybe the variable, instead of being at the numerator, should have been a denominator, or the power of the variable is wrong. So this analysis of variable by variable can give us some hints on what is wrong in the formula we generated from the data. Okay, so here you can see these three errors next to each other. So in this one, all these errors, as I mentioned before, they they give us kind of an indication first how good is the formula that we generated from data, how well it generalizes between the intervals of the data that we saw in the phenomenon, so we saw in nature, but also can tell us how well the formula generalizes beyond what we see in nature. Okay, so this concludes the first part in which I describe the like the system, how it works. And now I'll talk about 3 different problems that we analyzed in our work, and so that we published in the paper. So these 3 examples, we chose the 3 examples because they're all using real data. So we are not using simulated data. So real data is much more complicated to work with, as you probably know, because simulated data has a very kind of nice type of noise that we add artificially, while real data has first a lot of noise. Also, the type of noise is not as clean as the simulated one. And the second thing that I want to mention about this problem is that we consider a very small set of data points, like around 10 per problem. This is because often in like real world experiments, we don't have access to a huge amount of data. For example, the data that is required for machine learning models to train them, right? So then we wanted to kind of simulate real world experiments where each experiment or data collection is expensive, and or even observing the phenomenon is difficult. So the first example that I'm talking about is the Kepler third law of planetary motion. And this example is a little bit, so it seems simple, but in reality, it is not, because if we consider Kepler law of planetary motion, we consider like a body, a celestial body that is orbiting another body, right? So if we consider, for example, the solar system, the masses of the 2 bodies are very, very different. So when, for example, we add them together, the mass of the planets are basically 0 compared to the mass of the sun. So then if we consider just the data, we probably will not see that there are 2 masses. So there are some difficulties also in re-deriving Kepler's third law of planetary motion. For the second problem, this one is more is about chemistry. So this one is also difficult because it contains material-dependent coefficients. And the last one we used for the last problem, we consider Einstein time dilation formula. And this one is also interesting because we consider 2 different types of background theory. So the first one is Newtonian background theory, where we do not put a limit to the speed of the light. And the second one is relativistic theory, where we can say the speed of light is bounded. Okay, so let's start to talk about the first problem. So as I mentioned, Kepler's third law of planetary motion studied the orbit of a satellite against star, or a satellite against a planet, or even 2 stars. So there are different scenarios in which this law come into play. And the formula is what we see here, where we can see the P is the period of the orbit of the, for example, the planet, a planet around the sun. And this depends on the distance of the 2 bodies and the masses. And as I mentioned before, we consider 3 different data sets. Sorry, I'll quickly jump to here. So we consider 3 different data sets. So the first one, solar system. So we have just the sun and the planets. Then we consider also exoplanets, so different system of a star plus planet orbiting around them. And the third one is about binary stars, so 2 stars orbiting around each other. And these 3 different data sets have different difficulties. so for the solar system, the difficulty is that one of the two masses is the mass of the sun. So, and this is constant for each data point, because if we consider the orbit of one planet around the sun and the second planet around the sun, so all the data points, they have the first element that is the same. So then it's hard, just looking at the data, to produce this first mass into the in the function. So for the exoplanet dataset, so here we consider different set of system of planets orbiting around a star. So, and in this case, what is difficult is that the second mass is basically 0 compared to the first one, because even though the first mass, which is the sun, the star, it changes in different planetary system. The second one, the masses of the planets are too small to be compared to the mass of the star. So then when you want to add these two masses, the second one is basically impossible to add this mass into the formula, because the system will not understand that. So it will try to approximate this part, just considering the first mass, because the second one is basically 0 compared to it. So, and then we have a third data set for the binary star data set. So this one is, I mean, the two masses are different, so this one is a little bit easier, let's say, compared to the two. Okay, so here I just wanted to show you a little bit of the background theory that we consider. So we consider definitions that are known about the environment, like the definition of the center of mass, or the definition of the distance between two bodies, or the gravitational force, the centrifugal force, and so on. So then we run this system, our system, through the 3 different data sets. So first, we start with the symbolic regression. So the symbolic regression for each data set will create a list of hypotheses, and this one are ranked based on the error on the data. So now, once we have the list of hypotheses, then we run the reasoning component of the system. And this one will re-rank the list of hypotheses, and in this case was even able to say that this formula is derivable. So then if we look at the model complexity versus the data fidelity and the reasoning error, we can see we have different, very different plots. So in this graphs, the axis on the bottom is the model complexity, so it's how big the formula is. For example, this one here, so I consider just the last data set, so the binary star for simplicity. So equation 1 is very big, so the complexity is very high, right? But has a very low error on the data, probably because it's overfitting the data. While other formulas, they are, for example, equation 3, they have a much lower complexity. But, for example, equation 3, this one has a higher error on the data. But if we look at the model complexity versus the reasoning error, we can see that now equation 1 has both a very high complexity, but also a very high reasoning error, probably because the reasoner identified that this very long formula is overfitting on the data, so it does not generalize. So it just it's very good on the single data points, but if we look at the beyond, like between the data points, or even increasing order of magnitude of the domain of the data point, of the variables, then we can see that the error, reasoning error is very high. So then, looking at this, our optimization objective is in the corner, of course, with low model complexity, low data fidelity, and low reasoning error. We can see that when we re-rank the hypothesis using the reasoning error, the equation 3 is the best one. Okay, sorry, maybe I should have zoomed in before the explanation. But here you can see better that the equation 3 here is very close to our optimization objective, while in the data fidelity, maybe equation 2 was the best one. Okay, so here is the full table with all the reasoning error. And I just want to point out, for example, in the binary star example that we saw before, that this long formula, I just want to show you the actual reasoning and the numerical error. And we can see that the numerical error is the smallest, while the reasoning error is the highest for this data set. So then for each of these data set, we can choose the best formula that is approximation for that data set. And we can see that even looking at the dependencies, so when I look beyond the domain of the variable, this final formula that is also derivable is the one that has the best reasoning error, both pointwise reasoning error, generalized reasoning error, and dependencies analysis. Okay, so let's pass to the second example that I wanted to show you today. So this one is Lagomir absorption equation. So this one received a Nobel Prize, I think around 100 years ago. So we are kind of 100 years too late for this discovery. But this equation basically describes as a chemistry process, looking at how many gas molecules stick to a surface of a given material. So, and this depends on the gas, the pressure of the gas, and basically computes the loading, what's called the loading of the surface. So we can see here the graph of the ground truth formula that won the Nobel Prize. And we have on the bottom axis is the gas pressure versus on the other axis is the loading of the, basically the gas or the fluid on the solid adsorbent. Sorry, I cannot pronounce this. Adsorbent. Okay, so for this problem, we consider this background theory. It's very simple and has an equation for the site balance, the absorption rate model, and the desorption rate model, and the equilibrium assumption. And the final equation is about the mass balance. So we also consider an additional set of constraints. So the set of constraints are on the functional form. So I mentioned before the difference between the background theory and the constraints is that the background theory has variables that are not observed. For example, the site balance. You can see that here in the formula they want to derive, these variables, they do not appear, right? So we cannot observe this variable while doing an experiment, for example. While the constraints, they only involve the functional form itself. For example, we wanted the formula, the function with pressure 0 has 0. So no molecules are sticking to the surface if there is 0 pressure. Or if we wanted if there is positive pressure, then also the function is positive, and so on. Some condition at the limit and condition of the derivative of the formula, and so on. So, so we can see that there is this difference between the constraint that involves only the functional form and the variables that are observed in the environment, while the background theory is much more general. So then we run our system, AI-Descartes, on 2 different data sets. And the 2 different data sets, they have different gas and different material for the surface. And also they are performed on different temperature. And we can see that the blue dots here are the data points that we observed with experiments. And these lines are the formulas that we derived with symbolic regression. So just as a recall, here in the corner, you can see the ground truth functional form. So running our system, the symbolic regression part, we generate this list of hypotheses that you can see in the figure, and on the right here as like you can see the functional form of them. And while then running the reasoning component of the system, we can see that, for example, the F2 in the first dataset and the G2 in the second dataset are derivable. So here on the left, we can see that this is the orange formula. So we can see that both is passing through 0 and is approximating very well all the data points, while other, like F3, for example, first it doesn't pass through 0, so we lose that constraint, and is behaving very strange between two data points. So when we compute the reasoning error, the interval reasoning error here will be very high. So this is why probably the system chose the right one, because is the one that minimized the reasoning error. So for the second graph, we can see that G2 is derivable, which is the orange one. And as you notice, this one is not even passing through the data points. So this is why, so the reason why this is the case is that this is existentially derivable. So this means that the functional form is the right one, but the constants are a little bit off. So if we then rerun the system optimizing the constant, then we'll obtain the same functional form, which is this one, but with slightly different constant. And in that case, we will pass exactly through the data points. These other two formulas, the G5 and G7, so it's the purple and the pink one, these are not derivable, but they are satisfying all the constraints. So as you can see, they are very close to the data points. They pass through 0. They are both monotonic function and so on. So these are a good approximation, but the best one is G2 after we refine the constant, but still using the same functional form, which is derivable. Okay, so now I'll talk about a little bit the last problem that I was planning to show you today. So this is the relativistic time dilation formula. This, of course, also won a Nobel Prize. And so the formula is what we can see here in the bottom, and it relates the frequency of a light clock in two different scenarios. So the first one is a stationary light clock. So the clock is still. So you can think about having a light beam that is going to a mirror and then coming back. So and here the clock is stationary, so it's still. While the second scenario is when we have a moving light clock. So we can see that the light beam still hit the mirror and then come back, but then the distance is increased because the clock is moving, right? So in relativity, then you can see that there is like a dilation of the time. So the second one, the moving light clock, it seems to take longer time, right? So because the time is dilating. So if we look at the two background theories here that we consider, the first one is the relativistic background theory. So in this one, you can see that we consider C as bounded. So when we define like the space divided by the, when we define the time as space divided by the speed, say the interval of time, while in the second one, when we have the Newtonian axiom, we can sum the speed we can sum the speed of light with the speed of the clock. So these two are different between these two background theory. And here on the left, you can see an animation of how are supposed to be the two behavior of the two background theory compared to the stationary clock. So you can see when the stationary clock arrive, like the light beam arrive back from the mirror reflection. Also, the Newtonian has the same time of arrival, while for the relativistic, there is a dilation of time, so it takes a little bit longer. So the Newtonian one, then the two speed, the speed of light and the speed of the clock, they are summed together. So this is why the arrival time is the same. While for the relativistic, since the speed of light is bounded, then it takes longer, or it seems to take longer. So, so with our system, with the AI-Descartes, we can identify which one of the two background theory is explaining the phenomenon better, because we can run the system with one axiom system, so with one background theory, and to the other, and compare the reasoning error. So once we run the system, we can notice that for the Newtonian, using the Newtonian background theory, all the formula that we derive from the data have a very big reasoning error, while if we run the relativistic axiom, we can see that all the reasoning error are a little bit are better. So then we can identify which background theory is represented better by the data. Here you can see kind of the results of the top 4 formula that that approximate the data better. So in this case, we were not able to derive the correct formula, but we used the reasoning error to identify the formula that approximate the data better. For example, if we look at the generalized reasoning error, then we can see that we have a very low reasoning error, even with a very high speed that are close to the speed of light. While for other formulas, this is not true. So then we can see that even if in the cases in which none of the formula is derivable, we can still pick the best one, the one that approximates what we know about the phenomenon. So the one that is approximating the background theory also better. Okay, and just to conclude, I want to show you also a comparison of our system with the state-of-the-art system. So the 3 examples that I show you so far, so the Lagomir absorption equation, Einstein time dilation, and Kepler, they are based on real data. So all the state-of-the-art system, they instead work on simulated data. So simulated data, I think I mentioned at the beginning, is a little bit easier in the sense that the error, so the noise that we can see in the data is cleaner, and also we can decide which type of noise and how much noise introduced, while real data has a lot of noise and is not as clean as the simulated one. And moreover, for synthetic data set, you can generate as many data points as you want, while for real data, you're often restricted to like 10 data points or even fewer data points. So this is kind of the main reason why we mostly focus on real data sets. But we also, need to compare with the state of the art and see how we are doing on simulated data. And we can see that we outperform all the systems that we consider. And we consider a different type of system, like Feynman is a very famous paper from 2020 from Udesco and Tegmark. And this one is deep learning based. But then also we consider other type of systems using simulated annealing or evolution, like genetic algorithm and so on. And we can see that on this simulated data set, so this is done on fragment of the Feynman synthetic data set that was generated by the Feynman paper, we can see that we outperform all the other system quite dramatically, especially on the first cut of the data set. So this one is when we do not constrain the number of dependent variable in the observed variables, while in the second one, we had to focus on the one that are at most 2. So they are kind of easier problem. So the easier problem, also the other system are working quite good. But for when we consider more complicated problems with more variables, then we can see a drop of performance of the other system. Okay, so just to conclude, I want also to point out that we have released the code open source. So if you want to play with your own data or see how the system works in more details, you can go on our GitHub repository that you can see here. And also we have a nice website with a lot of animation and kind of like nice overview of the system and how it works if you want to know more details about it. And with this, I conclude the talk. And remember that next week also there is the second part that will talk about AI Hilbert that Ryan will be presenting. Thank you.
Yeah, thank you very much. Thank you. Any questions or comments? Yeah, it seems not. Yeah, I had a comment from a colleague who's a physicist. So we discussed a little bit before. He couldn't make it today, but his comment is that we are always discovering existing rules. But are there like rules that your tools can discover and then that extend existing physics? I don't know if it's clear or not. Yeah.
Yes, we didn't try to discover anything like new, but yes, this is totally possible. I think the bottleneck for like AI-Descartes specifically is having the background theory. So for but I saw some papers that, for example, take existing papers recently published, and then they try to work with that. But here for AI-Descartes, we have the assumption that the background theory is complete and consistent. So usually, like the background theory for this example that I show you, we knew it already and we wrote it by hand. So this is a little bit the bottleneck, but you will see next week that with AI Hilbert, which is the follow-up paper of this one, we removed this assumption, so then it would be a little bit easier. But yeah, please feel free also to, if you have some data, you can, and some background theory, you can also run the system yourself, and maybe you can discover something new.
I tried to convince him because I mean he works on quantum gravity and early data from early universe, and I was trying to see if but he was telling me that he saw these kind of tools, but he couldn't apply them because it's always about discovering something that is existing. But with the data that he has, there is no theory, right? I mean, they are still trying to develop a theory for it, and so he was wondering how it was not clear to him how he can use these kind of tools to guide the theory for this kind of data. Yeah, but hopefully he can make it next week. I mean, I already taught him about your series, but he couldn't come. Yeah.
Yeah, and we open source both this work and also AI Hilbert. So then, yeah, maybe he can try to run them, and please tell him to contact us if he has any trouble running the code.
Exactly. So I will. I just like CC all of you in next email. Yeah. All right. Yeah.
May I?
All right. Thank you. Yeah. Sure. Yeah. Thanks.
Hello. So
yes.
I missed some of your talk. but it's a bit of continuation. My response to Horesh, which was here a few weeks ago. And the question is, like, we have some puzzles in science, like, gravity and quantum theory. We want to reconcile those, and maybe these tools can shed some light on things which are really difficult. Okay, or for example, behavior of proteins in a very surprising way. I think the acid test for Descartes and tools like that will be to try on very difficult and puzzles in science, like open questions.
Yeah. And the beauty of AI-Descartes, it does not restrict to, I don't know, first order logic or equation. You can use any type of like syntax or format of the laws that you're considering. Just you need to integrate a proper reasoner, because the whole system is very modular. So we are actually looking for like interesting problems and try to solve them with our system.
Okay, beautiful, and good luck to everybody who tries this.
Yeah, thank you.
You're welcome. Thank you.
All right. Any other questions or comments?
Can you explain the difference between the Descartes and, I guess it was the Hilbert, I think was the other one?
Yes. Let me go back maybe to the slides. So it's a bit long. Okay. So yeah. So here, so in AI-Descartes, we have these two components that are sequential a little bit. So first we start with the data. So we use symbolic regression to generate a list of hypotheses from the data. And then once we have the list of hypotheses, we use the theory to find the best one. For example, the one that overfit the list, right? So for AI-Hilbert, we use polynomial optimization to put together these two things. So the optimization problem will contain both the theory inside the optimization problem and the data as well. So this is the main difference. Also, another difference between AI-Descartes and AI-Hilbert is that AI-Descartes, you could use potentially any sort of laws. So you can have first order logic, you can have equations, you can have polynomial equations, you can have differential equations, and so on, while AI-Hilbert focus more on polynomial equations.
So the Hilbert is not grammar based.
Sorry?
So the Hilbert is not grammar based, you're saying?
It's not grammar based. So it's still, I mean, it's grammar based. So it is the optimization problem is different. But I mean, you will know the details if you follow the talk next week. But we kind of formulate, we want to find a formula that is the combination of the existing formula multiplied by some polynomial multipliers. So it's kind of like, I mean, the grammar is enforced by kind of construction by the method itself, because we are just considering polynomials. So everything that can be produced is a polynomial. So I don't know if this answers your question.
Yeah, thank you.
Because in AI-Descartes, we impose the grammar in the how we generate the hypothesis. While in the AI-Hilbert, we just generate polynomials, which by kind of default obey to the grammar of polynomials, right?
It's a smaller subset of basic programs.
Yeah.
All right. Any last comments or questions? Okay, it seems not. Yeah, thank you, Cristina, for the nice talk. And so, as Cristina mentioned, the last part of this series will be next Thursday. So we're looking forward to seeing you then. Yeah. Yeah. Thanks, Cristina. Thank you. Okay. Bye, everyone.
Thank you. Bye.
Bye. Bye. Bye.